This is day 2 of section 2.6 in Algebra 2, and our objective is to analyze transformations of functions. Yesterday we talked about doing the translations, the slides, whether or not it was going to be up and down, right and left, or maybe a combination of the both eventually. And today what we want to do is add to that. What are some new pieces? And the new pieces are going to be talking about reflections and a few other things. So to start with, the reflection flips the graph of the function across a line such as the x-axis or the y-axis. And the second bullet here says the original points and their reflected points are the same distance from the line of reflection. Now that's a big deal. While I'm underlining this, it would be a good idea for today's lesson for you to have more than two colors of something. So, pencil, pen, maybe grab out of the bag some highlighters, colored pencils, whatever it is you need to do, because what we want to do is color code this lesson so that we can see everything that's taking place. Now, what you see for reflections here, where it says the original points and the reflected points are the same distance from the line of reflection, is what you did in geometry last year, which means we're going to reflect it over a line or a point, depends on the problem. And what we want to do is make sure that we go equal but opposite on the other side of the line. So that distance stays the same, like it says, same distance from the line of reflection. Two really important ones are going to be reflecting in the y-axis. Now, when we reflect in the y-axis, that's something I want to think about a little bit. So let's just say that I have my x and y axis, and I take a point on this side, and I want to reflect it over the y-axis. What I realize that means is I'm going to have to go straight across the y-axis, equal but opposite on the other side. So if I think of my first blue point here as 1, 1, when I get done, I want to go 1 unit to the y-axis and 1 unit further, and that would make that the point negative 1, 1. And then I notice, well, look at that. Only the x coordinate changed to a negative. And it should, because when you reflect in the y-axis, your x values are going to change signs. Your y values are going to stay the same. And like it says, our normal graph, well, now we're going to have a negative in front of the x coordinate. So that's what happens when you reflect in the y-axis. You can think of it as y-axis. Let's see, I have to use the opposite. That means I need a negative x-axis coordinate. So we're just going to say y-axis negative x. Then, if we come over to this other side and we see that we're reflecting in the x-axis, and I'm going to go back up with a different color, and I'm going to look at my point 1, 1 that I had here, and I'm going to think about reflecting that equal but opposite over the x-axis. And I realize I'm still going to go from the origin 1 to the right, but now I have to go 1 down. So that'll be 1, negative 1. So when I reflect in the x-axis, the x values stay the same, but the y values change sign. So I'm going to put negative y right here. So when we reflected in the y-axis, we made the x negative. When we reflected in the x-axis, we made the y values negative. Now notice down here that it says f of x becomes negative f of x. Y, remember, is what f of x stands for. The output, just fancy function notation, becomes negative y. So to reflect in the x-axis, the y becomes negative. Now go back and look at this one. That's not the whole thing being negative, that's just the x being negative. So reflect in the y-axis, x becomes negative. Reflect in the x-axis, y becomes negative. And that's what they did in this little drawing down here. They're doing the same thing that I showed you with the really basic point of 1, 1. They're going to use an entire graph. So I look at this and I realize, well, this one in the black, that's the original. That's f of x. That's where they started. To get to the blue one, I notice, hey, they went equal but opposite on the other side of the x-axis. So that was a reflection of f of x in the x-axis. And then I think, okay, x-axis, reflect over the x-axis, the y becomes negative. So instead of this being 5, 1, it's going to be 5, negative 1. Well, that makes perfect sense. Instead of 3, 4, it will be 3, negative 4. Yeah, all they're doing is making the y negative. If we have this 2, 2, that's going to be down here at 2, negative 2. And if we have 1, 1, that's going to become 1, negative 1. Reflecting over the x-axis makes the y negative. Now don't look at the blue one anymore. Instead, we're going to look at the green one here, which says reflection of f of x in the y-axis. So we go back to this one again, but this time we think, now I'm going to go equal but opposite over the y-axis, and that makes the x's negative. So instead of being 5, 1, this should be negative 5, negative 1, and it is. Instead of this being 3, 4, it should be negative 3, positive 4, and it is. Instead of being 2, 2, it should be negative 2, positive 2, and it is. And instead of being 1, 1, because it's in the y-axis, I change the x-coordinate to negative 1, 1. So those reflections, think opposites. Reflect in the y-axis, make the x negative. Reflect in the x-axis, make the y negative. Because we're not always going to do this with graphs, with these nice visuals that we see here. Sometimes we're going to have an equation and we have to think, how do I make this reflection happen when I'm talking about an equation? So problem 3 says, let g of x be a reflection of f of x equals 3x plus 3 in the y-axis. What is the function rule for g of x? Okay, well, let's start with f of x. F of x equals 3x plus 3. The first thing I do is change that to y so that I can think about what this graph is going to look like. And I'm color coding this one. I'm going to make this a black line. And I know it's a line because it has x to the first. And when you have an x to the first, that's linear. So with this one, we would start at the b value because this is y equals mx plus b. We would start at 3. On the y-axis, that's our y-intercept. And then our slope would be 3, so we would go up 3 and to the right 1. And I'm going to do that a couple of times, and I'm going to use the slope backwards so that I have something to aim at, and I get a fairly straight line. Now, this one is f of x, so this is not my answer, but I want everybody to see when we reflect this what happens. So I'm going to go ahead and label that one f of x. Now, what was I supposed to do? Well, it said way back up here, we want to take f of x equals 3x plus 3, and we want to reflect it in the y-axis. So I think, okay, I have this, and if I'm supposed to reflect that in the x-axis, that means I have to make its opposite, which would be the x, negative. So I'm going to have to put a negative in for x and make this 3 times negative x plus 3. And I think, well, that's silly. 3 times negative x is going to be negative 3x plus 3. And now that I have this in blue, I have this in a different color. Notice that I changed colors to graph the second one. I'm going to go ahead and graph this in blue to see what's happening. So y equals negative 3x plus 3. I think about my y equals mx plus b again. Hey, this one also starts at 3. But its slope is negative 3. So I have to go down 3 and to the right 1 from that point. And I can use my slope backwards and go back 1 and up 3 to give myself something to aim at for my straight line. And then I remember they wanted me to name that g of x. So I'd better not keep my equation as y equals negative 3x plus 3. I have to rename it because they told me what they wanted it to be. So now I'll write that as g of x equals negative 3x plus 3. And I look at that and I think, you know what, that makes perfect sense because they wanted me to reflect over the y-axis. That means the x becomes negative. So here it was, all positive, and here it is now negative, which is exactly what we wanted to do. So notice the little bullets up here that walk us through this. It says, for a reflection in the y-axis, change the sign of x. That's what I did right here. Changed that sign to negative x. Evaluate it and simplify. Well, I didn't want to leave that there. 3 times negative x. This looks incredibly goofy. I have to simplify that to negative 3x. And then, like it says, check by graphing to make sure that you have something that's giving you a reflection in the y-axis. So I go back to my graph and I think, yep, look at that, equal but opposite on the other side of the y-axis. So yeah, that's my reflection. Even down here, you can see equal but opposite over the y-axis. This is 1 unit, this is 1 unit. This is 2 units, this is 2 units. That's how it's supposed to work. So to reflect in the y-axis, change the x, make it negative. Now, the got it says, and I'm going to go ahead and change colors one more time here and use that same axis that I had up there. Let h of x be the reflection of f of x equals 3x plus 3. Oh, well, I'm going to use y. And then it says, let it be a reflection in the x-axis. So if it's a reflection in the x-axis, that means I have to make the y negative. Oh, I can't leave it like that. It's going to be much easier to graph if y is all by itself. So what I'm going to do is either multiply or divide the whole thing by negative 1. Most people look at that as being multiplied times y, so it's easier to just divide everything. But really, what we're doing is we're taking the opposite of everything, by having that negative y out in front of there. So it's going to be a negative 3x minus 3. And then I remember they said, uh-oh, give it a new name. Call it h of x. So we're going to call this one h of x equals negative 3x minus 3. And that's important. If they tell us what we're supposed to name it, that's what we need to name it. Now, let's keep that same color and let's go back up here to our graph, where this time we notice we have to start with that y-intercept at 0, negative 3. And then we have to go 3 units down and 1 to the right, because our slope was negative 3. And again, I'm going to use that slope backwards, so going back 1 and up 3 a couple of times to give me something to aim at. And there's my red graph, which is h of x. So we had to reflect that one in the x-axis. And I think, well, okay, what did they want us to reflect? They wanted us to reflect the black graph right here, this black graph over the x-axis. Well, that makes sense because any points that are on the x-axis, you learned this in geometry, they're not going to go anywhere. If it's 0 units from the x-axis, well, then you make sure it's 0 when it's reflected. But when you take a look at this, you realize, okay, so if I have to reflect this over the x-axis, I should end up with my little red graph right there to show me that equal but opposite piece that I need to have when I'm reflecting. So that one started at negative 3 and went down 3 and to the right 1. Now, if you're thinking to yourself, okay, that visually is not working for me. What do you mean, Cedarholm, when you say equal but opposite? Here is the x-axis. Make this blue right here. And my red and my black have to be equal but opposite from that. So I think that's a pretty good grid point right there. I think you can see that this distance to the x-axis is the same as this distance right here to the x-axis. And that's what that reflection does, equal but opposite on the other side. So like I said, really good to have this color-coded because then you can do the whole page on one graph and you can actually see how all of those different transformations, that's the big name for what we're doing here. Anything that you translate, stretch, compress, any of those things are going to be called transformations. So now we need to talk about vertical stretches. And vertical stretches are what would happen if you took your graph and you made it out of rubber bands and you put one hand at the bottom of it and one hand at the top of it and you pulled up and down at the same time. You would stretch that out. So what happens with those, and I want you to look at this graph that they have right here. This blue one is the original. This was f of x. So when I look at this, I can see that the red one was a stretch. They grabbed that blue graph wherever it was not touching the x-axis, and they stretched it out. That made the red one, and notice that one's labeled a times f of x. So some number a, when you put it out in front there, makes that stretch. So like it says, the x values stay the same, but you're multiplying all of those y values by a number that's greater than 1, a factor that's greater than 1. So when we see these, and we see that there's a number out in front that's bigger than 1, then we know we have a vertical stretch. That's what we're looking at today. But then I see the green one. And I notice the green one is kind of the opposite. So you have your graph, your blue graph, it's made out of rubber bands, and you decide to squish it. And the fancy name for that squish is called a compression. So you're squishing that graph. But if we were making it bigger, since we were multiplying by a number bigger than 1, what on earth do we have to do if we want to multiply by something and make it smaller, compress it? And notice this says 1 over a times f of x. Now that means when we see a fraction between 0 and 1 in front of our function, then we're going to know that it's going to be a compression. So stretch, number bigger than 1 out in front of our graph. Vertical compression, because vertical means up and down, so remember this is what I said with the rubber band, where we're actually putting our hand at the top and at the bottom and we're pulling those apart. With vertical compressions, we're pushing them back down together, we're shrinking it. So the x values stay the same, but notice this is going to reduce all the y values, this was a green one up there, by a factor between 0 and 1. So if we see our graph, we see our equation, and we see a number in front that's a number between 0 and 1, then we know we have a vertical compression. Now, this is really nice math language right here, and it says that our number has to be greater than 0 and less than 1. We've talked about compound inequalities. We know that's what that says. But for most people, it helps to think about it as a fraction between 0 and 1. So if I see a 2/3 in front of my equation, I say, oh, that's a fraction between 0 and 1. That's going to be a vertical compression. If I see 5/3, no. 5/3 is not a fraction between 0 and 1. 5/3 is bigger than 1. That's going to take me right back up here to a vertical stretch. So don't just think because it's a fraction that that's going to be a compression. You have to think about the fraction. Is this a fraction between 0 and 1? Problem 4 says the table represents the function f of x. What are the corresponding values for g of x and possible graphs for the transformation g of x equals 3 times f of x? So I'm going to use green on this one. 3 times f of x. Well, that means this should be a vertical stretch. Now, how did I know that? Because there's a 3 in front, and 3 is a number that's bigger than 1. And I also know that in order to figure out where this graph is going to go, I don't change the x's. The x's are going to stay exactly the same. What I have to do is take 3 times everything in the f of x column, because I'm stretching out the y's with a vertical compression, because vertical is up and down. So I'll take 2 times 3 and get 6. Negative 3 times 3 is negative 9. 3 times 1 is going to be 3, and 3 times negative 2 is negative 6. And now this is kind of a strange little graph, because we're used to making sure that, things are in a line or they're a parabola or whatever. Not this one. We don't know what the original function was. Now, why do I say that? Look up here. They just called it f of x. They didn't tell us what f of x was. So here's what I want to do. I'm going to put f of x on my graph, and I'm going to do this in black. So I'm going to underline that one. So how I graph that is just by graphing negative 5, 2, negative 2, 2, 0, negative 3, 3, 1, 5, negative 2. And like I said, normally we'd say, oh, let's just connect all this stuff up in a line or a curve, but not this one. So what we have to do is make lines, straight lines, from each point to the next point that's to its right, because graphs are read from left to right. And we will call this one f of x. Now I already started on the other graph, which was called g of x, with green. So I'm going to use green for this one. Now I have to go all the way back to the original x's. So I'm going to have to graph negative 5 and 6. 1, 2, 3, 4, 5, 6. Negative 2 and 6. 0 and negative 9. 3, 3. And 5, negative 6. And again, I'm going to connect this up with straight lines from left to right. And as I'm doing it, I'm thinking, wow, that is definitely a vertical stretch right there in g of x. So if we took that black graph and it were made out of rubber bands and we just stretched it by a factor of 3, we would land at g of x. This one's kind of crooked. That's a little better. Not much, but a little. So now, they have another one down here. We're going to need to grab a different color. This one says for the function f of x in the previous problem, what are the corresponding table and graphs for the transformation h of x is 1/3 f of x. So I'm going to change colors to blue here. And I'm just going to add a column to this table, remembering that it said 1/3 of f of x. So now I'm going to go back to that f of x column right here. And I'm not going to think 3 because 3 was a vertical stretch that I had to use for g of x. I'm going to think 1/3. So 2 times 1/3, well, that's going to be 2/3. That's going to be for both of those. Negative 3 times 1/3 is negative 1. 1 times 1/3 is 1/3. And negative 2 times 1/3 is negative 2/3. And again, I'm going to graph these with the original x's. And then now that h of x, that's going to change the vertical component, the y component. So at negative 5, we're only at 2/3. At negative 2, we're at 2/3. At 0, we're at negative 1. At 3, we're at 1/3. And at 5, we're at negative 2/3. And now again, connect those up with straight lines, left to right, and call that h of x. And we can definitely see that that one was a compression. It's like taking the black graph f of x and squishing it down, making the bottom and the top squish the graph down to give us the blue graph in h of x there. So that's called a compression. Some books will just call that a shrink, a vertical shrink, but the fancy language for it is a compression. So now, it says problem 5, the graph of g of x is the graph of f of x equals 4x, compressed by a factor of 1/2, and then reflected in the y-axis. What is the function rule for g of x? Okay, well, let's see. I'm going to start with f of x equals 4x, but I'm going to remember that's y equals 4x. That's what that really is. And then if you want to compress by a factor of 1/2, you have to put a 1/2 in front of your equation. So I'm going to use a red here. So I have to do that. But I know what 1/2 of 4 is. It's 2. So now this would be y equals 2x. Not done though. They didn't say just compress it by a factor of 1/2. It said then reflect it in the y-axis. Okay, reflections, you have to do opposite. So if it's in the y-axis, the x becomes negative. So it'll be 2 times negative x. Oh, that's silly, because that's going to be negative 2x. And lastly, they did not want me to call that y. It said this was a function, so what is the function rule for g of x? So g of x equals negative 2x. Now notice that just like we talked about before, you don't want to get too hung up and confused by the f of x, g of x, h of x, all of that stuff. Change it to y right away, do all of your math thinking, and then at the end you can put it back into whatever name they want it to be, whatever fancy function notation they have. Now B says, what transformation changes the graph of f of x to the graph of g of x? So we're starting with this, and we're supposed to tell them, how did it get to be this? Well, let's see. It was a 2x squared. What do you do to 2x squared to get it to be 6x squared? Oh, you multiply it by 3. What does it mean when you multiply something by 3? It is a vertical stretch by a factor of 3. That's what that is, a vertical stretch by a factor of 3. Now, in Algebra 2, we are not going to talk about horizontal stretches or compressions. That's strictly pre-calculus, college algebra pre-calculus level. So all of ours are going to be vertical stretches or compressions. Because that was multiplying by a 3, and a 3 is bigger than 1, that's going to be a vertical stretch. All right, that wasn't it though. Because if that were it, 2x squared times 3 would be 6x squared, and we would have been done. But there's a minus 1 hanging out in the back there. Okay, minus 1. Oh yeah, that's the number in back that moves it up or down. So this would also be translated 1 unit down. That would do it. That would take the 2 in front of the x squared and make it a 6, and then the minus 1 in back would definitely move it down 1. Got it. And speaking of got it, if you want to give yourself a little try here, you could certainly pause the video and see if you can do this one on your own. So this one says the graph of g of x is the graph of f of x equals x. So starting like this, and f of x is of course y. Stretched vertically by a factor of 2, all right? So that's what I had, but now there's going to be a 2 in front of it because it has to be vertically stretched by a factor of 2. And then it has to be translated down 3 units. Down 3 units. Well, that would be you're taking the whole graph and you're subtracting 3. Well, there it is. That's the function rule for g of x. Because again, those numbers in the back, all by themselves, are for up and down. And up would be plus, and down would be minus. So g of x equals 2x minus 3. Go ahead and, again, if you want a little bit of a challenge, stop the video and give B a try. And then you can start it back up and I'll show you how it works. B says, what transformations change the graph of f of x equals just x squared to this, the quantity x plus 4 squared minus 2. All right. Well, this is still x squared, but there's a plus 4 in there. Okay, hang on a minute though. That's attached to the x. And things that are attached to the x are backwards from what we normally think. Plus actually means it's going to the left, and minus means it's going to the right. So if this is a plus 4, that means this went translated 4 units left. That's the one we have to be careful of. The translations that are attached to the x. Notice how there's parentheses there. That is attached to that x. We have to think backwards. Not the numbers in the back, which brings us to minus 2. That one is just normal. We think, okay, a plus is up and a minus is down. So this is also translated 2 units down. And I don't see any other numbers that would be affecting this graph that we didn't already deal with. We dealt with the 4 and we dealt with the minus 2. So left 4 and down 2. And that takes care of our objective, which was to analyze transformations of functions. In fact, not only have we been able to tell them what the numbers are doing to give us those transformations, but we've also been able to write them, which is fantastic. So now you're going to need a little practice. And that's what 2.6 day 2 is for. So go ahead and pause the video and write this down, and you should be able to work through the rest of this.